Welcome to qnawire.
Okay, we're looking at question 28.66. We have two wire semicircles that are connected here to make a current loop. And we're trying to find the net magnetic field that the current in the wires produce at this point. So this point is a distance A from this inner semicircle and distance B from the outer semicircle. Now the first thing to notice, well, let's take a look at the Biot-Savart law, which is what we're going to need to use to calculate this. And the essential component is this dl cross r. So dl is going to be along the length of this wire, and then r will be the vector pointing from the point to the point on the wire. And if we take a look at this, notice that these little horizontal components are not going to contribute anything to the magnetic field here, because the cross product between dl, which is along either the plus or minus x direction, is parallel to r, which is also along the plus or minus x direction. So these two components we can just totally ignore because they're not going to contribute anything to the field here. So let's start by just going ahead and calculating the magnetic field from this first part. So let's just basically copy this over here. We're going to get, let's say that we're defining current to be positive in this direction to the left along here. So we'll get positive I, and then dl cross r is really just going to be dl times r, because if we notice, since this is a semicircle, it's not drawn very well, but since it's a semicircle, it's going to be perpendicular to the tangent, which is dl, is going to be perpendicular to r, which is going to be the vector pointing to the center of the circle at every point along this. So dl and r are going to be perpendicular for all points here. And that means that the cross product is just going to be equal to the regular product of their magnitudes. So we're going to have dl times r here, and then a factor of r cubed on the bottom. So right away, we can just cancel out one factor of r, leaving us with r squared. And notice that r here, since we're looking at this inner one, is just going to be equal to a. And now these are all things that we don't necessarily know the values, but we're told what I is, and we're told we have a. So now we just need this dl. So I'm going to pull this factor of dl out, because what we're going to need to do is integrate over this expression. So I'm going to just hold off on that for a minute, because now what we want to do is add to the we want to add the component of the magnetic field from this second outer part. So the outer part is just going to be the exact same thing, except what we have instead of a here, this is just going to be b. And we know that, again, regardless of which direction we define the current in, we'll decide the direction of the magnetic field in a minute. We know that it's going to give an opposite contribution as the other one. So I'm just going to say that this I is going to be negative. So let's call this minus, because we know these aren't going to just add total. We know that one is going to be bigger than the other. And again, we'll figure that out in just a minute. But what we need to do at this point is integrate this to get b. So we're going to integrate this dl. That's why I pulled that out, and integrate this. Integrate this over here. So when we integrate db, that will just give us the total b, which is, of course, what we want. So that's great. And then when we integrate dl, for this case, it's just going to be the whole circumference of the circle that we're going around would be 2 pi times a. So half of that is just going to be pi times a. And similarly, the integral over here is just going to be pi times b. That's going to be the length of this outer semicircle. So we're going to have total b will be this. And then, like I said, this part is going to be pi times a. And similarly, the contribution from this part, again, I'm making this negative just sort of arbitrarily, is going to be b, and then this is b squared. So we can simplify this here. We have a factor of a on top and a on the bottom. So let's get rid of one of those. B again, we're going to be left with only one factor of b down here. We also have a 4 pi down here and then a pi up here. So I'm going to cancel those out as well just to make these calculations a bit easier. So this is basically what we're left with here. If we wanted, we could even factor out this mu naught times I, since we see it in both cases. So we have mu naught times I and then 1 over a minus 1 over b. And again, let's figure out, we know that a is smaller than b, so let's figure out which direction we actually want here. If we want to make this a positive number, then we actually would want to flip this direction, make this all negative, because b is greater than a. But let's determine if we know that b is, a is a larger number, which means that 1 over a is going to be a bigger value than 1 over b. So this, when we just plug in numbers for this right away, this is going to give us a positive number. So this is going to give us the magnitude of the magnetic field at point P here. And just thinking about it, we know that the closer wire is going to have a stronger effect on the magnetic field because it's closer to point P here. So thinking about the direction that this wire, the direction of the magnetic field that this wire is exerting on point P, if we point our thumb in the direction of the current at A, so point our thumb along counterclockwise like this, using the right-hand rule, we find that that means the magnetic field is pointing out of the page here. And that means that the contribution from B will be pointing into the page. But again, we know that A, this smaller one, is closer since A is smaller, which means that this contribution is going to dominate. So we're going to have, if we have this, a positive magnitude like this is the magnitude of the magnetic field, and it's going to result in a magnetic field that's net out of the page.